So if two objects are pushing on each other, so when an external object pushes on the chosen object, it applies a force that's perpendicular to the surface of contact and toward the chosen object. Okay, so let's think about two objects that are in pushing contact. So let's say that there's a block. Let's actually make it, give it wheels so it's easy to imagine it without any friction acting on it. And let's say it's in contact with a ball. Okay, and let's call, like a sphere. Let's call this body 1 and this body 2. And let's say that there's some force of 10 newtons applied to this one. I'm going to draw free body diagrams of each of these. So first I'm going to draw a free body diagram of that little cart thing. So assume that that's the chosen object. So there's the outline. And the force is acting. There's a weight force that's equal to the mass of that, I'll call it M1, times 9.81 meters per second squared down, so M1G. And we know it's acting downward. And then going around the boundary now for the contact forces, the ground is pushing on the wheels, okay? How do we know that's a pushing force? Because if the ground wasn't there, the cart would merge into its space, okay? So that's a pushing contact that's preventing those two things from merging. We actually have one of those at each wheel, but for now as particles, we can just treat it like it's a single one. I'll call this N1. I'm going to use that variable N a lot for normal force, but really that's not conceptually important. You just have to know that that's a variable representing the magnitude of that pushing force. And then on the right side, that ball is pushing on this object. It's pushing because that contact is preventing them from merging. So there's a force this way, perpendicular to the surface of contact toward the chosen object. And I'll call that R. Keep going around the boundary, and the last thing is the given force of, and we don't have to know what's providing that. The work's already been done for us, so 10 newtons of force that way. Any questions about that? So we had two pushing contact forces there, the one from the ground and the one from the ball. Yeah.
Why are you labeling that R on the right? What's the significance of R?
Oh, R is for reaction. So again, conceptually, it's not important. You're just giving it a variable name, but N's and R's are normally used for pushing contact forces, but it's just a variable. This is the last thing, so, and then we're done. free body diagram of body 2. So this is the ball. There's a weight force that's equal to the mass of the ball times g. And now go around the boundary looking for contact. There's a pushing force from the ground, and I'll call that N2. Keep going around. Over on the left side, there's a pushing force coming from the cart. And now, notice that pushing, the force the cart applies to the ball and the force the ball applies to the cart represent this pair of contact forces between two objects. And when you have that, when you're just switching from the contact force on from 1 on 2 to the contact force from 2 on 1, they have the same magnitude. We'll talk about that more later on. But whatever the value of the first one is, that's the value of the second one. That's going to be a super useful thing. It's actually called Newton's third law, and we'll get to that. Okay, last thing. Just notice this one last thing. What about that 10 Newton force? That's right. Like, this can be a little confusing because whatever motion happens from that ball is going to depend in some way on that 10 Newton force. But when you're figuring out the forces that apply to this, all you're doing is putting in the forces that are acting around the boundary. This 10 Newton force isn't acting on the boundary of this, so it doesn't show up. It does show up indirectly. If you increase that force, it'll make that R force bigger, but it doesn't directly influence that. It doesn't directly apply to the boundary, so you don't put it in there. Okay.